So good afternoon everybody, myself Acharya Vishwendra. Let's continue on NCERT line to line discussion, chapter 14, semiconductor electronics. So let's begin with the question number 149. It says that charge on n-type semiconductor is, so they are neutral, so there is no net charge, so third is correct. Next is charge on p-type, it is also neutral, zero charge. Next is dopant atom of the p-type semiconductors can be treated as, so they can be treated as a core of negative charge with its hole as depicted in the diagram over there. So first is correct. Next is for a p-type material, holes are majority carriers, electrons are minority carriers, both are correct. Third will be correct over here. Next is in p-type semiconductors recombination decreases number of, no, there are actually more number of holes, so they will decrease the number of electrons. So second is correct over here. Next is in p-type semiconductors, number of holes dominates, so second will be correct over here. Next is a p-type semiconductor is obviously it's neutral, third is correct over here. Next is in p-type semiconductors, charge of additional charge carrier is obviously it is equal and opposite to the ionized core, so that makes things neutral. Next is in extrinsic semiconductor, by doping intrinsic concentration of minority charge carriers. Extrinsic semiconductors by doping intrinsic concentration of minority charge, obviously it decreases. Next is in extrinsic semiconductors by doping energy band structure is affected. Obviously energy band structure so in extrinsic semiconductors at room temperature most of the donor atoms gets ionized, this is correct, and a very few atoms of silicon gets ionized, this is also correct, so third will be correct over here. Next is in extrinsic semiconductors, conduction band will have most electrons from, so obviously most of the donor atoms gets ionized, so most of the electrons will be from the donor impurity, so first is correct over here. Next is for p-type semiconductors, the acceptor energy level is slightly below the bottom of conduction band or slightly above the top of the valence band. So certainly it is slightly above the top of the valence band. So second is correct over here. Next is for p-type semiconductors, while acceptor energy level EA, electrons from the valence band can easily enter EA. Yes, they can easily enter EA. So first is correct over here. Next is in p-type semiconductors, for EA level we can say that holes from EA level sinks to the valence band or electrons from EA level sinks to the valence band. So we can say that since there are holes, so we can say that holes from EA level sinks to valence band as so one will be correct over here. Next is for extrinsic semiconductors. So this equation is approximately valid as per the experimental data is concerned. So first is correct over here. Next is the above description is it's approximate. Next is difference in resistivity. It depends on energy gap between the valence band's area of cross section. So it depends on the energy gap because resistivity is independent of area. It's dependent on the material only. Next is energy gap for carbon, silicon and germanium are. So this is corresponded by the first thing. Next is energy gap for stainless is about. So stainless is about metal. So it's 0 electron volt. Next is for N-type semiconductors, band gap between EC and ED is. So the band gap for N-type semiconductors so the gap between EC and ED is about 0.01 electron volt. And for P-type semiconductors, the band gap between EV and EA, this is in the range of 0.01 to 0.05 electron volt. Next is a pure silicon crystal has these atoms per meter cube doped by pentavalent impurity. Calculate number of electrons and holes given that Ni is equal to this. So assuming that all the atoms are ionized, so there are 10 into 10 is to power 28 atoms. So if you calculate the concentration comes out to be about we can say that there will be 10 into 10 is to power 22 total pentavalent impurities, assuming all of them contribute to the conduction. So this will be the number of electrons generated, which will be very greater than intrinsically generated carriers. So by using this, if we calculate Ne, Nh is Ni square. So Ne is approximately 10 is to power 23 into Nh, and Ni is 1.5 10 is to power 16. So whole square is 2.25 10 is to power 32. So from here Nh comes out to be 2.25 into 10 is to power let's say 9. So it's corresponded by the first option here. Next is basic building blocks of diodes and transistors are. So it's a PN junction basically. Next is 175 external applied voltage in a junction diode is called, it's called the biasing. So first is correct over here. Next is when a small quantity of pentavalent impurity is added to a p-type semiconductor wafers, then obviously it will form a p region, n region and a metallurgical junction between p and n. So third is correct over here. Next is two important processes that occur during formation of a p-n junction are. So these are diffusion and drift, both are opposite to each other. Next is concentration of electrons means its number of electrons per unit volume. Third is correct over here. Next is during formation of p-n junction, due to concentration gradient across p and n sides, electrons diffuse. So electrons are more in the n side, so they'll diffuse from n to p, whereas there are more holes on the p side, so they will diffuse from p to n. So third is correct over here. Next is diffusion current arises due to, so this is due to the concentration gradient. First is correct. Next is when it electron diffuses from n to p, it leaves behind. So obviously when it will diffuse, so it will be an ionized donor on the n side obviously. First is correct. Next is this ionized